In this video, we're going to talk about how we can calculate some sounding parameters through the use of MetPy functions, as well as plot some other unique items on our SKUT image. To begin, we're going to be working at part 2 of the handout that begins on page 4. And specifically here, we want to use the Advanced SKUT notebook. So let's go ahead and duplicate that, send it to our working notebook. Go ahead and rename it here. Sounding calculations and plotting. Again, you can name it what you want. And boy, did I really mistype that. Got a 0 in there for an I. There we go. And we'll go ahead and launch that. And so again here, we have kind of the same beginning here aspects of all the import statements. Again, don't forget to change your kernel to be Valpo Spring 2020. We'll have to wait for that to update here. There we go. And then we can go ahead and run our import cell, grabbing our data, and then isolating our variables that we want. And so as it's doing that, let's go ahead and talk a little bit about these calculations that we can do using MetPy. And so in the conceptual videos about this topic, you learned about how these are actually calculated and what some of their significance is. But let's go ahead and click on this link here to then look at all of the different functions that we can calculate here for sounding specific pieces. So for example, we see things like bulk shear and LCL and parcel profile. There's a whole bunch here. And these all work on sounding related data, and a number of them require different amounts of data to go into them. And so, for example, one of them that we want to start with today is this one called LCL, or the lifting condensation level. You may remember the lifting condensation level from Met 103 as the level at which a parcel lifted will reach saturation. Typically, that means a surface parcel, and that's the mode that we're going to use here. So we can click on LCL to see what the elements are that go into it. And so we can see there are 3 main inputs: the pressure, the temperature, and the dew point, all from the starting position. Now, typically what we want to do is we want that starting position to be the first element in our arrays, because that will be the surface value. Now, technically you can do it from any level, but then you're going to be assuming that your parcels are being lifted from that level, whichever it is. And so that's why, for the purposes of weather technology this semester, we want you to use surface-based parcels. So let's go back. Okay, so our data has now loaded, and we now get to this first cell here where we're going to do a calculation. And so here we're calling from mpcalc, so from MetPy calculation module, the function LCL, and we are now feeding it our pressure, our temperature, and our dew point. And the way that we're specifying that first surface level parcel is by adding the square bracket 0 to each one of our variables. That's allowing us to isolate just a single value. And so if we go ahead and add in a cell here, we can print P0, T0, and TD0, and see that these are the values: 950 hectopascals, 21 degrees Celsius, temperature 16 degrees Celsius, dew point. That is what's being fed into this function here. And then what's being output, if we go back to look at our documentation, are 2 things: the pressure of the LCL, so basically how high up in the atmosphere is the LCL, and the temperature of the LCL. And so we can unpack those 2 things into 2 separate variables, one of which I'm calling LCL pressure, and one which I'm calling LCL temperature. And the one that I care most about is what pressure level is this LCL, because that tells me how far up above 950 hectopascals it's going to be. And so calculation runs really quickly, and we see that the LCL is at 849.72 hectopascals, or basically 850 millibars. So we see it's a bit above the surface. And so we can calculate this variable and just output it. We don't even necessarily need to plot it. Another calculation that is very common that we want to do is to calculate the parcel profile. So what the parcel profile is it is the temperature of a parcel that a parcel would have if lifted from a given surface. And so in the instance that we're going to use here, we're going to lift a surface parcel. So a parcel that begins at ground level and then goes up and traces the path, the temperature path of that parcel as it initially lifts dry adiabatically when it is unsaturated and then moist adiabatically after it is saturated. For more information on drawing a parcel profile and what it means physically in the atmosphere, I refer you back to the videos on that from Adam. In terms of how we're going to use this and how we can calculate it within MetPy, we have a function to do that. Our function in this case is parcel_profile. And so we need to feed, again, 3 things into this function. The same 3 things that we fed into LCL, except with one slight variation. Our slight variation here is that we need to feed it all of the pressures that are from our sounding. And so again, if we go ahead and print P in this case, you can see we have a lot of different pressures. And the reason we need all these different pressures is because we want to calculate the parcel temperature, what it would be at each one of these pressure levels, so that when we go to plot it up, it makes it really easy to do so. Otherwise, then we're going to just feed it our starting temperature and starting dew point values, which happen to be from the surface in this case. And what we're going to get out of this function is a unit array, of which we want to have those units be in deg_C for plotting purposes and for interpretation purposes. Otherwise, it will default to Kelvin, which is fine, but might be more useful to us. And so this is going to give us back then a profile's worth of temperatures. Once we've calculated that, we need to use that to feed into then our calculation for calculating CAPE and SIN. And so CAPE and SIN are the area of our SKU-T that is bounded by our parcel profile temperature and our actual temperature profile, T, or our environmental temperature. And so we need to feed it the full arrays of pressure, temperature, and dew points with our parcel profile in order to ably calculate both CAPE and SIN. Again, 2 things are going to come out of the CAPE and SIN function, CAPE and SIN, and we can unpack those into separate variables, CAPE and SIN. And so let's go ahead and run this cell. We can see it goes pretty fast. There's some integration that has to go on to do this, especially to calculate CAPE and SIN. And so we can print out just the results here. And this sounding, it turns out, has 1,973 joules per kilogram of CAPE, but at this time, nearly 232 joules per kilogram of SIN. And so the reason SIN is negative is because it is negative area. It is where the parcel path is to the left of our environmental temperature profile. And it's energy that we have to gain to overcome to realize the CAPE that's there. We're going to go ahead and plot up this profile, this parcel profile, in just a second. But before we do, we want to get to one more value to calculate. Now this one, there is not a function to be able to read or use from MetPy. But really, it's just a simple difference function. And so lifted index is the temperature difference between the parcel and the environment at 500 millibars. And so the critical piece here is just figuring out, well, where in our array is that 500 millibars? And so that's what this bit of code is doing here. First, we're making a list out of just our values of our pressure by using the .m, the magnitude there. And then we are using a method off of our list called .index to find out where in our list does 500 appear. And so that's going to give us an index value that we can use to then compute the difference between our parcel profile temperature at that particular point and subtract off our environmental temperature. And that is our lifted index. Boom, we see our lifted index is 6.18. That's pretty high. That means there's pretty good instability, which we also measure through this CAPE. And so, again, a lot of this is about developing corroborating evidence through these different common SKU-T parameters. To plot our SKU-T, we're going to use largely the same information that we used last time. So to plot up our temperatures and our dew points in red and green, to plot our wind barbs, and to plot our limits here, I'm going to go ahead and change this again back to 40. To plot our parcel profile, we use this dot plot method again. And here we want to again use our P because we have our parcel temperatures at each of the P levels. But instead of feeding it the environmental temperature T, we're going to put in here our prof variable, which is our parcel profile temperatures. And we're going to plot it in black. This K here means black. And we're going to say it's a line width of 2. We want it to stand out just a little bit. Additionally, we're going to plot our LCL level with a line marker. And so that is done through this code here, where we take our LCL pressure and our LCL temperature to get the Y and X value. And we're going to plot just a short line in the color black with a size of 24 and an edge width of 3. Again, plotting all of our common variables, we can go ahead and run this cell. And so they see that we've now added this black line, which is our parcel profile temperature. And so we see this area above this level here at about 600 and maybe 70 millibars or so. This area is that CAPE area that was represented by the calculation we did above. And this negative area here, since our parcel profile is to the left of our temperature profile, our environmental temperature profile, this is the SIN. And so that minus 200 and some SIN seems appropriate. And the about 2,000 joules per kilogram of CAPE seems about appropriate given this profile. There are other things we can change about this plot. For example, if we wanted our dew point to be some sort of dashed line, all we need to do is to come up here and add line style equals dashed. Probably line style. There we go. And so it's dashed. But now maybe that's a little hard to read compared to the other dashed contours. So maybe we could say it's dotted. You can see what that looks like. Oh, that's good too. But now maybe line width equals 2 to make it just stand out a little bit more. Yeah, and that stands out a bit more. Again, this is part of map making where you get to test your own things that you like and the ways that you want it to, in fact, look. That's it for this video. In a future video, we're going to talk about how we can read local data in order to plot soundings, say from a Valpo launch. Thanks for watching.